Assuming the forcing function on a spring mass damper system is of the force F naught times cosine omega t, one can take the steady state solution to be equal to A times cosine omega t plus the phase angle phi. After taking the derivatives of the steady state solution and plugging them into the equation of motion to solve for A, one gets the following answers for A. After plugging this answer for A into the steady state solution, we can take 1 over the denominator of this function and call it the amplification factor. The amplification factor is often defined as the ratio of steady state amplitude to the static deflection amplitude.
So here we have the underdamped case, which zeta is between 0 and 1. On the top of this slide is the general expression for this case. And we have already calculated xt before and also the xxt in the previous lecture. And we have got two unknowns here, C1 and C2. By using the initial condition, we can solve those two unknowns and get the final expression for this case.
Here is the equation of amplification factor AF. The first case is when omega approaches to 0. AF will be equal to 1 for all damping ratios, because when you plug in omega equals to 0 into the AF equation, you will see the value of AF is independent on the damping ratio, and the denominator becomes 1. Since the final value of AF is 1. The other case is when omega equals to omega n, plugging the ratio of omega and omega n, which is 1, then AF will be 1 over 2 times the damping ratio. And notice that as the damping ratio approaches to 0, AF goes to infinity based on calculus.
We also talked about resonance frequency. Resonance frequency is the frequency at which there's a maximum amplification factor for when zeta does not equal to 0. To find an equation for this, we had to find the derivative of the equation for AF. After replacing the ratio omega over the natural frequency with the term x and deriving the equation 3.99, we were left with the equation 3.107 from the book. Then we were able to solve for x once we set the numerator equal to 0. Knowing that we can ignore the answer x equals 0, we were able to find the final equation for the resonance frequency in terms of zeta and natural frequency.
Lastly, we did the steady state displacement. The steady state displacement could be associated with the phase angle. It is the difference of the position of a point, for example a peak, in the forcing function and the steady state solution. Since both the forcing function and the system response have the same frequency, the only difference is the phase angle. If the phase angle phi is negative, the equation for t becomes positive. This means that the steady state solution is going to lag the forcing function. In the case above, the steady state solution lags by a phase angle of negative pi over 4. On the contrary, if pi is positive, the system leads the forcing function by the amount of the phase